Assalamu alaikum. Can you please finalize your attendance sheet and just sign on one place? Because I have seen like few of the people, they have signed on maybe first page or second page and then on last page as well. So only sign at one place, then it will be easy for us to see all of the days or how many sessions you have attended. Because I need to send this back so we can get the certificate template. So, and also if your name is not very clear, please try to write in capital. Otherwise, I will assume how I understand it. Okay, so let's start from where we left yesterday. We discussed the different kind of seeds we have, like the seeds which can identify the nodes, and there are kind of seeds which identify the adjacency, and then the third type of seed it was which can identify the group of nodes, and we say they are representing one group, and this is called the ANICAS group. So we have like there is any segment identifier seed for the node. We say it is to identify the node. But if we want to use for a certain link, then that would be for the, we say it's a adjacency seed which represent a link. There are a number of nodes which are part of one group. Then we say these are the part of ANICAS group. So the instruction related to this ANICAS group, we can use the one label, and then any one of any of the nodes which are part of this group. Once they receive the packet and the top label is the label which is the ANICAS label, then they can process it and send the traffic to the other side. So without we have discussed how the segment routing can work, what are the different use cases as well. So one of the requirement for segment routing for sure, or one of the very strong use cases to use it for the traffic engineering within your network. Either you have customers, like you have VPN customer, or maybe you can use it for your own customers. It does not necessarily needs to be VPN customer to do the traffic engineering. Even within your own network, if you have like multiple paths, you can use the traffic engineering to send the traffic from one side to another side. And there are so how we can define the traffic engineering? The traffic engineering is ability to send the packet on a certain path, and this path could be the IGP path, like the shortest path, or it could be not the IGP path, and it could be based on certain criteria. So the different criterias that we have, like other than the shortest path, one is like the IGP metric, this becomes the shortest path. Other is TE metric, this also could be the shortest path based on the TE metric. Latency, like on your links you have certain latency, and we can use this as a criteria. We can use the loss, like if there is any packet loss on the links, and we can use this as a criteria. The last one is the link coloring. That's mean within our network we can color the links, and then we can specify, okay, use the links which have this color, maybe red, green or blue. So then it can use those color and calculate the path automatically. Or you can say, okay, exclude these color, then it will exclude all the links which are having those color, then it will calculate. And there is another way, like maybe you can specify the hop count, like how many nodes should be there. So it will count the, it will take the path which have the lowest number of nodes. And obviously you can specify include and exclude as well. So the traffic engineering policy, how it is like realized in terms of business, it could be the SLA, and it could be like our intent or wish or our requirement as well. So If you have other customers, maybe your internal customer or external customer, because sometime in case of like campus network, you have internal customer, like maybe the students, maybe other departments you have, which are your customer and you are giving them services or you are carrying their traffic. So you would have some sort of SLA with your customer, like when you are giving service to them, your uptime will be this, latency will be a certain number, and the availability. So this could be your SLA. Another way is like the coloring. As we said, we can say, okay, we are going to use the certain color, and then we can attach this, like I'm just going to write our service on a green links or on red link or blue links. So within the network, first we have to color our links, and then we can use we use the color to like make the policy. So let's go back to our example network. So it's a little bit different than the previous one. So now we have like the CE routers attached to the P routers as well, and in the middle we have the core network, and you can see like few of the links, they have their color is green. You can notice the SIDs and the sRGB as well. So it is the same sRGB. That means it will be like it's will be globally unique or globally significant. So this is so our purpose in this case is we want the lowest the traffic should go over the lowest latency link, and the shortest path is blue, but the lowest latency path is purple, and the green links for them the color is red. So this color on the right hand side, this is our intent for the policy. This is not the color of the links. The color of the links is like green, but this one color we are saying I'm going to use the red color, so this will represent our policy. But the coloring of the link is the actual color we have defined on the link, which we define in sort of like bits, and then we can say, okay, I can build a map like affinity map, and there I can specify, okay, number 20 will represent green, 30 will represent red, or 40 will represent like maybe pink or any other color. And then on the interface I go and specify the color. But when we create the policy, then in every policy we use the color. So the color in this table you are seeing here, so this is the color for your policy, and the other one, this is the color on the links. So when we are creating the policy, we are assigning a certain color to the policy, and this will be based on that we can identify our policy. So how we can route the traffic over the path? So we can say we have the lowest latency path based on our previous. You can see this is the shortest path because this has the lowest metric in our case. So by default, if the traffic needs to use the shortest path, then it is going to use this path. So we have so in this case the traffic will go over the shortest path, because we will if we need to send the traffic over shortest path, how we were doing, we were just putting the label for our destination node. Okay, so any node in the middle, it's going to receive the label for the 222. It's going to route it accordingly. We do not need to specify anything else because we are using the shortest path. So in this case, P1 will push two labels, service label, transport label, and based on the topology or the network, it knows, okay, this is the shortest path because here the IGP metric is 20, and from other links you can calculate it will be like 30 and 40 from the other two links. So that's why this become our shortest path based on the metric. So in case of lowest latency, it will go over this path because we have it has calculated like lowest latency, and we know like this path has the lowest latency. So we have to put in this case the SID list for the nodes which are in between. So what could be our SID list or list of the nodes that needs to be traversed before the traffic reach to P2 in this case. So there should be only total 3 SIDs in this case, because P4, P5 and P3. So we are making sure here traffic does not go to any other path. We are making it like a strict path. So it is going to then follow the shortest latency path or lowest latency path. So once the packets come in, we need to, we have created the policy. Within the policy we have specified the labels for the P4, P5 and P2. So it will be 104, 105 and 222. So at the top, which label will be? So once the policy is created, in the SID list, which label will be at the top? Yeah, 104. P4 will process the top label or the active segment. Yesterday we have this question in the quiz as well. So it will, since 104 is the local SID, so it will just pop it and then send the packet to the next node. So P5 will process same and it will reach to the P2 and then to the destination. So the last one we have the traffic engineering. Same in the same use case, how we can optimize our SID list. In this case, we know if we reach to P2, P5, then the traffic will go to P2 based on our metric. If we calculate from here 10, 20, 30, and this is 10 and 20. So that means I do not need to put the SID for the P4. If I simply put the SID for P5, it will go to P5 and from there it will go to P2. So based on the metric, this could be our optimized SID list. So in this case, the P4, it will just swap, P5 will pop and P2 will also pop 2 times and then send the traffic. So same thing we can do with like less number of SIDs as well. So in order, if we need to use the links which are colored as a green and we want to use this path, then we need to include the nodes which are part of this green path. So in this case, it could be like 4 SIDs, or maybe we can optimize this as well. So you can see initially what our thought will be, like we have to put like 4 SIDs, P1, P2, P3 and P2. Okay, they will process based on the top level and then traffic will finally reach to P2. I'm just going a little bit fast because we have done this a lot of time. So I hope it's okay for you as well. So what could be the optimized SID list in this case? Okay, so you are saying 102, this one, and finally this one. Why not we just put P3 and P2? Because if we reach to P2 and from there if we calculate the metric, it will be like 20 onward, and if it goes through any other path from like here to back, or it goes from here, so still it will be 10, 20, 30, 40, and from here it's just 20. The other one, it's obvious that it's more than like 20. So if we put just P2 and then P2, still we will be able to reach to the destination. So in this case, our intent or our intention was to use only the green links, and in order to use the green links, we can just put the label for the P2 and then PE2. How you can reach to P2? Our intention is to reach to P2 and use this path. Make sure we are going over this path. So how we can do this? The first very simple way, we can put the node SIDs for all the nodes which are coming on the path, and it makes it very strict, and we are done. The second is like how we can optimize it. Like instead of doing maybe a not very efficient way, how we can do with the less number of SIDs, because the more number of SIDs you put, the device next, the upcoming device, it needs to process it, and if you put less number of SIDs, obviously this will make impact on the processing, and maybe we have like improve the performance and we do not include or burden the nodes which should not be part of it. What we can do, as we saw earlier, if we just put the SID for P2, then it goes over this path, because based on the shortest path it will use this path. But our intention is to not to use this path. We want to use the links which are colored as green. One way is like as I said earlier, I can put the node SID for all the nodes which are coming in between, P1, P2. Obviously we have to put for P2 as well, because this service is attached here. But I'm saying how we can optimize it. So when I'm saying optimize, that means I do not want to have 3 labels. I'm just thinking, is there any way I can achieve the same thing by using less than 3 labels, maybe 2 or 3 or 1. So then the option is, we can one suggestion was to put the SID for P2, like we can put 102, and second we put 103, and then we put the 222. Why we are not putting for P1? Because we know from if we put 102, from here to here the metric is 20, and from all other links, if we calculate from here, if it needs to reach to P2, it will be 40, and for sure from here it will be again 10, 20, 30, 40, 50. So that's why if we put P2, automatically it is going to use this link. Until unless there is any change, we remove any link, but we are considering this is our network. If we put for P2, it will reach to here. Now next one is 103. Obviously it will go to 103 and then P2. But we are saying, okay, if you do not put 103 and P2 directly consider it is sending to P2. So it will, based on the shortest path, if P2 is not there and only the 222 is there, so now P2 will calculate the shortest path from PE2, and you can see it is 20 from here, and from other links it will be 40, and again it will be 50 here. So that's why if we put just reached up to P2, then after that, based on the shortest path, it will reach to P2. That's why we are not putting the P3 or 103. I hope it's clear for everyone. Okay, let's put 103. If we put 103 and then the 222, okay, so let's do the routing. So P1 will see how it can reach to 103. So it will calculate the metric 10, 20, 30. It will reach, and from other side 10, 20 and 30. So now two paths are equal. But our intention is to avoid this link, not go over this link. What will happen? It will send one packet from here, the second packet it will send from here. So although we will be able to reach to P3, but our intention was to only use the green link. That's why we are putting 103 instead of 102, because in that case our requirement is fulfilled. So 102, then it will go to 222. So this is how you can there are different ways to fulfill your requirement, and we need to understand why we are doing something and does it make sense as well. So we have discussed this question, why is the SID for P2 required in the segment list? Why can we not use P1 or P3? This we already discussed. So in case of when we are creating the policy, or how we can do the traffic engineering, there are different ways. Like one is we can do using the segment routing policy. Another is we can use the flexible algorithm. Due to the time, we will not be able to discuss this topic. This is like you can specify some sort of constraints, and then based on your specified constraints, the segment routing policy, it will calculate the path. So first you have to specify your constraints on the network, and then this is sort of we say flexible algorithm to calculate the traffic engineering. Seamless MPLS, this is a solution. Like in the middle you have the segment routing, on the edges you have the LDP, so you are able to provide the MPLS service without having any issue. Whatever the service will come through, the segment routing will be able to carry it on. But again, due to the time, we cannot discuss it, unfortunately. So why we need to optimize our list? Why it is important for us? Because the devices in our network, they can have a different capability to process the like the maximum segment depth could be different on different devices, and in that case we have to think about, or we have to consider what is the minimum segment depth that our core network or the devices who are going to take part in the segment routing domain and obviously in the policy, what is the segment depth, and we should honor that and keep our segment list of segment to support this. So this is again typically, I said, it's a vendor base, so it depends on the hardware and the feature they are providing. So there is a mechanism to reduce the segments, like number of segments, and we can use the traffic engineering policy, and within the traffic engineering policy we can use the BSID. So in that case, what will happen if I go back to our example? So if I create a policy, like we have a certain requirement where we create a policy which goes from P1 up till P2, okay, and we maybe the requirement is to put, okay, this may be not relevant, so maybe there is a requirement like we have to put the 2 segments or 3 segments, and this node can only support 2 segments. So then we can create another policy on this node, and we have like maybe 3 or 4 nodes afterwards, and our final destination is somewhere here. So if I create like a 7 segment list, so these 2 devices, they cannot process it. So in that case I have to create 2 policies, one I create here, another one I create here. So what will happen once the traffic reach to P3, it will see the top segment, it will remove and then attach another policy. So it will replace the list of segment based on the policy that is matching with the segment which it has received from the PE1. So this is called the BSID or binding SID. In that case, the router who receives the traffic with the binding SID, once it receives, it can actually then attach the new SID list based on the binding SID it has. So that is another way to deal with the issue if you run out of the support for the list of segments. So in case you are using a controller and then the controller is actually calculating the path, and in that case the controller needs to know what is the capability of each device and what is the maximum depth of the devices. So we share this information with the controller, then actually controller computes the path accordingly, so it satisfies the requirement and it is within our constraint or the limits. So we actually give this information to the controller using the PCEP, and when the PCEP gives us the path, then it actually fulfill this requirement. So how we give this information? We give using the IGP, OSPF or ISIS, and or we give this information using the BGP to the controller as well. So when controller is going to discover the topology and it's going to receive all the information regarding the nodes and their capabilities, so then actually it can calculate the path accordingly, keeping in view the constraint we have. So again, OSPF and ISIS, they are similar. So there are some TLVs which are actually used to support this information or to carry this information. One of them is like the router information OPAQ SLA. Like I said yesterday, there in case of OSPF or ISIS, we say SLAs, they are used to share the information about the devices. who are taking part in the IGP domain. So another is like how you share with the controller. If you are using BGP instead of ISIS, then it will use the node attribute TLV to carry it. So how this information is shared? So if this is our network and this is the controller. So we can see here we have 3 domains, like this is one domain and this is another domain and this is another domain. When I'm saying domain, that means this is routing domain. This is not the autonomous system number. This is the routing domain, like we have multiple areas within the same network. So from each domain, we need to share the information with the route reflector. Maybe you can have 1 or 2 routers which act as a route reflector. It's a kind of a proxy router which actually receive the information from each of the area. Once it receives, then it can use just one single BGP session to share this information with the controller. Otherwise, the other option is you run directly IGP session from each of the area from within that area with an ABR router, and that router is going to share with the controller. So instead of doing this, the BGP has more control, where you can put even the policy not to receive any route advertisement from the controller if there is even any mistake. So you do not accept any routes, you just share the routes with the controller. Because in case of OSPF or ISIS, you do not have any control to apply a policy on the route advertisement. You cannot filter the routes because you share the LSAs, and those are not in form of routes or prefixes. But in case of BGP, we share the prefixes. That's why we have the ability to filter the route. And as a organization, or if you have any network, we never advise this to run OSPF with any other organization. You should only run within your domain or within your autonomous system number. Because if you are going to run OSPF from your organization to another organization, either ISP or another university, so actually all of the routing information for your complete network is going to be exposed to them. And then he do not need any information from you. He can just take that output and draw complete of your network. Because if we take the link state database, we can see which are the different OSPF neighbors and what are the links connected with each of them, and we can even draw on the paper. So you will be like exposing something which is your internal information. But since controllers is also it will be your ownership, but the better way is to run the BGP LS instead of the IGP. How each of the node is going to share the information internally, and then your ABR, which is going to share with the RR. So it will share in form of a BGP LS MSD, and then it is going to be shared with the controller. So from each of the domain, the information is collected using the IGP, then it is like redistributed into the BGP, and then BGP is going to share with the controller. So next up we have like what is shared. So we share the traffic engineering information. The traffic engineering database is shared, and it contains lot of parameters like the link interface, remote interface, traffic engineering metric. Like we saw in the policy, we can use the traffic engineering metric like the IGP metric to calculate the shortest path. So we can calculate the shortest path based on the IGP metric or based on the traffic engineering metric as well. And you are going to share the unreserved bandwidth, maximum reservable bandwidth, and the shared risk link group as well. So all of this information, whatever is the part of traffic engineering database, this is going to be shared. So this is the explanation for each of them. So we are also going to share the traffic engineering database for the IGP as well, and this is the information which will be available within this. So here you can see unidirectional link delay. So based on this information, it will be able to see what is the latency between two links, because based on the latency you can also calculate your request the policy. And how the link loss was coming, like we saw in the what are the different criteria that can be used in policy. So link loss is one of them. So once the controller will have this information, obviously then you can request to controller to calculate the path. Otherwise, if you are manually creating the policy, then each of the router is going to satisfy this information. So this is the information regarding the traffic engineering extensions we have. So there are RFCs. If you are more interested, then at your own time you can go through them. Again, the traffic engineering extensions. So these traffic engineering extension, these are like not new ones. We have been using for the RSVP protocol. Remember, before the segment routing, when we need to do the traffic engineering, we were using the RSVP protocol. And so this information, since it's already there, that means now it will not be only the RSVP protocol which is going to use the traffic engineering extension, it will be the segment routing as well. So they are going to share this information. So the traffic engineering attributes, these are actually now advertised, and they are required for the SR policy, they are required for the flexible algorithm and the loop free alternative as well. So that means when there is any kind of loop, maybe due to the link failure, so the device need to send to traffic to the destination avoiding the loop. So then this information will help to calculate the path. So as I said earlier, like there is no way to advertise different values. You have to use the same attributes for the all of the different protocol which require this information, like RSVP and the segment routing as well. So how we can like identify them? We can use the application specific codes or attributes if we want to. So we can distinguish for which of the application we are using what information, and then device can actually calculate the path accordingly, and it can identify like what is the bandwidth has been used for RSVP, how much the bandwidth has been used for the segment routing as well. So there are two key elements to associate the link attribute and advertise the link specific application as well. And we can also use the advertisement of different values for each of the attributes for the different applications. So both the OSPF and ISIS, they have the capability to like advertise this. Again, we have the link attribute TLV if we when we want to advertise this information. And if there is like if there is a new application, obviously if we have the shared risk link groups TLV, so it is going to carry this information for the SRLG. In case of ISIS, this is not, I think, supported for the OSPF. So there is also TLV. I will not go into detail for the TLVs, and if you need, then I will leave it to you to read them later on. So how we construct the segment routing policy? Like we saw earlier, that we can have like maybe three kinds of different policies to use for the link. Green links we can use for the lowest latency, we can use for the shortest path. But how this is getting implemented in case of segment routing, let's see that. So in order to define the policy, we actually define the order list of segments, and then that is a way how we can express our policy. But in order to send the traffic over the link, we can maybe have a when the traffic comes into the ingress node, then the packet needs to be sent over the policy, and then this policy is going to be selected to encode the packet, and each of the packet will be going to use this policy. That means when the packets come in, we need to identify which policy we need to use for this packet. So there should be some sort of criteria that we can use. Okay, when the packet is coming, maybe we can attach a community and advertise to the other side. So when other side is going to send the traffic, it can see, okay, I can use this policy to send it. So usually these policies, they could be applied to both the segment routing MPLS and segment routing IPv6 as well. So in order to identify the policy, like there could be more than one policies, so how we are going to identify each of the policy? There are three elements within the policy. One is head end, color and endpoint. Head end is your first node, which is the ingress node. The color is the color we assign to the policy, and endpoint is our destination node. So based on these three things, we can uniquely identify a policy. So the name of the policy, this could be the symbolic name, this could be the any name, and then we can have a priority within the policy. Like if we, this priority is going to determine, like if we have multiple, like which one is going to be selected as a best, and maybe we can configure the segment routing policy based on the highest priority, and then within that we have the candidate paths. Like within the policy we can have the path, and then we can specify the preference or the priority against the path, and it is going to use the path with the highest preference in that case. And the lowest preference path, this could be your backup path. So if the highest goes down, then it's going to take the other one into effect. So this is the construct of a policy. The example, like the symbolic name, this could be segment routing policy 1, just a name. How we can identify head end, color, endpoint, and the priority. So within the policy we have the each of the policy is going to have paths. So there could be one path or more than one path could be specified within the policy, and each path is going to have the list of segment. You can express the list of segment as the labels, or even you can specify the IP addresses. So the type of candidate, it could be explicit, dynamic, or composite. When we are saying composite, that means combination of both explicit and dynamic. In case of explicit, obviously you have to give the list of the segments, but in case of dynamic, you can just specify any of the optimization objective. When you are saying optimization objective, that means maybe you can specify lowest latency, lowest metric, hop count. So this could be your optimization objective. In that case, it is going to automatically calculate which are the different links which can fulfill this optimization objective. Or even the controller, it can calculate the path based on your optimization objective. So the head end router, it will learn the candidate path. It can learn the candidate path via the configuration, or through the PCEP, or through the BGP. So these are the different different ways to give the input of the path. When we are saying configuration, that means as a network engineer, as a operator or admin, you can by yourself configure the path, or it could be through the controller when we are saying through the PCE or BGP. So the first one is manual, the other two is the dynamic way to calculate the path. So the candidate path, they are identified within the segment routing policy, and they can only exist within the scope of the policy. So we can have like how we can identify different paths, like it could be identified based on the protocol, based on the originator and the discriminator. So in case the protocol origin is the how this path has been learned, so this could be your origin protocol origin, and the originator is the node that is actually going to signal this path where the candidate path has been configured. So this will be your head end node, and the discriminator, this is a 32-bit value to actually identify the path within the policy. So we can differentiate different paths that have like same, maybe other two parameters are same, then we can use the discriminator to identify it. So let's see an example for the segment routing policy, like how within the segment routing policy, if we have two paths, how they look like. So like we can have a policy, name, identity, priority, and then we can have a two paths, and they can paths could be identified based on the three parameters we have. Again, the candidate path, it can have a symbolic name as well. Like each path you can give a name, and then you can give a preference to select which one of the path you want to prefer. The highest one, it will be preferred, When you have multiple, then you have to specify the list of segment, and if two paths have the same preference, then you can specify the weight in order to give this information, like how much portion of traffic should be carried by a certain path. So maybe you want to have like 50% or 60% traffic or 80% on certain path, then you have to increase the weight accordingly and keep the other path weight like maybe up to 20. So we can say like the symbolic name of the path, identity, priority. In this case we can see they have the same priority. Preference, so this one has the highest preference. So in this case the router is going to select this path because based on the preference, and then within path we have to give the list of segments. Okay, so it has first list we have specified like S11, 12, 13, and then whatever it could be S1N, and we are saying weight 20 and then weight 30. So based on that, this is going to carry the more traffic and this is going to carry the less traffic. So it is going to use both of these paths, but the traffic distribution will be based on the weight. Here maybe we will have like 2/3 and here 1/3. But if this path goes down, if this path is not available, then the segment routing policy is going to use this path, and then based on the segment list within this path, it is going to use them, and then it will distribute the traffic according to the weight we have specified here. Any question you have? So as I mentioned earlier, the binding seed is the actually useful to reduce the list of segments when we face the issue of maximum segment depth. So in that case, the binding seed actually help us to deal with the this limitation, and it actually allows the topology internal to the domain. It's hidden. You are not going to use it for the if someone else is sending you the list of segments, obviously you are not going to honor it. So this is related to only to your network. So the recommendation is to use the binding seed value for the candidate path and particular segment routing policy as well, and the segment routing policy is going to inherit the binding seed of the active path. Like if you do not specify, then it is actually going to use whatever the B seed for the active path, it will be assigned to the policy. So we can see here we have the candidate path name, identity, priority, preference, segment list, and then the B seed is 1000. So this, because since this is the candidate path and if it will be active, then it is going to be assigned to the policy as well. So how we use it? So you can see this is our service label. So we put the binding seed and then we put the node seed as well. So once this node is going to receive this list of segments, so it will process the top segment. If it belongs to it, then it is going to pop it and send the traffic to the next node. Otherwise it will just swap and send to other node. And once it reaches to the node who has this binding seed, then it's going to expand this 1000. It will remove 1000 and attach a new list. So it will pop 100, and then because in this case 1000 is also configured on the same router, it is going to replace it with this list. So after that, our new seed list, it will be based on the binding seed we have. So it's kind of mapping you have created, because you have created the policy. Within the policy we have specified this seed list, because remember in the path we have calculated earlier, we have specified this seed list. So that's why it will replace the 1000. It will replace 1000 with this list of segments. So this is how you can optimize, again, send the traffic, and maybe the policy is not configured on the first node, it is somewhere in the middle of the network as well. So this is the example, like how if we put everything together. So you can see B seed B1, both the candidate path, they have the same B seed, because one of them is going to be active at one point in time. So we can have a dynamic candidate path. This was the example of explicit. So we can have a dynamic. So in case of dynamic candidate path, we have to specify our optimization objective, and that could be a constraint, or which actually we are going to satisfy. We can say the lowest latency, lowest metric, or we can specify a certain color as well. So a path that satisfies the objective together with its constraints has to be computed by headend or the PCE, which is like our controller. So headend mean the router, the ingress router, either it has to calculate or the controller needs to calculate, and they should satisfy the constraint we are specifying, and we are going to achieve our optimization objective. So the one of the ways is could be like the min metric. We are going to request the path that is like on the minimum metric between two nodes. So it could be the IGP metric, TE metric, or the latency metric. So within the dynamic candidate path, we can also specify the constraints in order to like narrow down, or in order to make our choice more exclusively. So in that case, we can specify some of the constraints like traffic engineering affinity. This could be the colors, the IP address, or the shared risk link groups as well. We have some tags specify, or the maximum number of seats we can specify. The part should have a certain maximum number of seats. If the number of seats goes beyond that maximum number, then it can exclude that path. So this is the how this would be calculated. So in that case, we can give the requirement to the controller to compute the lowest latency path between router 1 and router 15. So this is our router 1. This is the source or the head end, and this is the tail end. So we want to have calculate a path, or we are asking controller to give us a lowest latency path between these two nodes. So instead we calculate by ourselves, we are asking the controller to give us this information, and we have this also information like the metric. All IGP metric are equal to 10, and we have not, I think, specified any other metric. So that's mean all the links, they have the metric 10. So how the controller is going to know this information, like the metric configured on the network, it is going to get this information through BGP-LS, and within BGP-LS we have the IGP extension where we share the T enable, like using the traffic engineering database, we share the latency and the loss information and the other information, like we saw in the case of TLVs, like we share a lot of parameters, and using those parameters, the controller is able to know about the network, and then it can fulfill this requirement. So once we have shared using the BGP, then controller has the maximum knowledge about the network, and then it can like have similar to like link state database. Obviously it will have the link state database for the both of the domains, and it can calculate the path. So after that it will actually give us a policy, and it will like be able to identify, like in case of a policy we have 3 parameters. What are the 3 things to identify a policy? So what is R1? What we say R1, or what is R1 in our case in terms of MPLS nodes? What kind of node this is? Head end. So that's mean this is the head end. One is head end, color, and the end point. So this is how the policy will be created. Then we have to specify the priority, and then candidate path. Our objective is minimum metric in terms of latency, and we have not specified any constraint like anything else, like exclude these links or colors or something like that. So it's just going to check the lowest latency from the R1 to R15. Request to the controller, and then controller will compute the path, and it will give us the list of segments to which satisfy our requirement. So it will be 1, 3, 4, 5, 12 and 15. So 1, 3, 4, then 5, sorry 6, I have to 1, 3, 4, 6, and after that it's saying go to 12, and after that go to 15. So this is the lowest latency path. Although we can think of about this, but I think there would not, so 10, 20, 30, 40, 50, 10, 20, 30, 40, 50, 60. So it will be 60, that's why it is using this. But in terms of latency, actually it's not the metric, it's the latency. So this could be the other links because latency could be different. But we are saying minimum latency, in this case it has to provide. 1, 2, 5, 6, 12, 15. Yeah, it could be same, but what we have said, we are saying latency, not the metric. Minimum metric in terms of latency. So latency is like how much time it takes to go from one node to another node. So that we have to consider in this case. So we can say IGP metric, we can say TE metric, or we can say latency metric. So the latency metric, that means latency metric will not be equal to the IGP metric or TE metric. So it will be different than the metric we have, because maybe a link, the metric is 10, but the latency could be there 100 or 90 or 50. Just to clarify it again, okay, let's suppose this link is at ISB, okay, and this is maybe Karachi, and we have a direct fiber link from here to here, and this link is from ISP to RWP like Rawalpindi. If even I specify metric 10 here and metric 10 here, so in order to reach from here to here, the latency would be I think 60, and here maybe we have a latency 5 or 10, maybe less than 10. I don't think it will be 10, less than 10, because it's nearby, because every 100 kilometer it takes 1 millisecond on the fiber. So this is nearby, so it depending on, like, maybe we have 5 devices in the middle and each device is going to take 1 millisecond, so it becomes 5 in that case. So now if we calculate the metric 10, 20, 30, and we are reaching from Karachi to maybe Quetta, okay, and we are going somewhere to MLT like Multan. Okay, so this is 10, 20, 30, and this is 10, 20, 30. So even they are equal in terms of metric, but for sure from ISP, if you are going to Multan, latency will be low from here. So it will be higher from here because we are first going to Karachi. We are going through, although just passing in front of Multan somewhere, and then going to Karachi and then coming back. So metric would be different and latency would be different. I hope it's may be more clear now. If not, we can discuss afterwards. So based on this information, we will get the list of SID list in order to satisfy our requirement, and then the router is going to use this policy, and it will be able to send the packet over this policy. The packets who needs to be sent, there should be some criteria to select this path for certain packets. How we select the best path? So your best path would be one of the, it would be the active candidate path, and the candidate path that is selected as a best, so one of the path is selected as a best path. When you have multiple like candidate path, it would be your active path, and this active path actually it's going to be primarily or mainly used based on the preference or the and if there is a tiebreaker between multiple candidate path, then you are going to use the highest preference value to select the best path. So only active path is used to forward the traffic and then send the traffic over it. So your backup path is not used, but we have seen like within the active path even we can have multiple seed list, and we can attach the weight if you want to use the multiple path within a single candidate path. If you are wondering, what I am saying is like, so we are saying these are two candidate path. One of them will be active at a time based on the preference value, okay, and only the active candidate path is going to be used to send the traffic. So within this, even if you want to diversify, you want to use two paths, within a path you can attach the segment list, two segment list, and you can specify the weight if you want to distribute, or you can specify like maybe 10-10, so then they become equal cost path. So then both of them are going to share the traffic. But it will not happen that this segment routing policy will use this path and at a time use this path as well. It is going to use only one and not this one, because here we have the preference is less, and in this case higher preference is preferred. So another thing we need to consider when we have the dynamic path, we can and we have enabled the TILFA. Again, this is another topic we will not be able to discuss. This is actually used to have the protection within the segment routing. So if we want to protect our traffic within the segment routing domain, we have to enable the topology independent loop free alternative, and it actually allows us to protect the individual segment or the list of segment of the active path which is specified within the segment routing policy, and each segment is like individually and locally protected. So what I was saying, if we enable the segment routing policy and we have specified our path is like this is our lowest latency path, okay. So what if we lose this link? If this link goes down, maybe this will not be appropriate in this case. If I say this link goes down, okay, and we have enabled the link protection, or we have enabled the TILFA, sorry. So in that case, what node 12 is going to do? It is going to send traffic towards 13 or towards 9. Maybe it can send traffic towards 13 or 9, but if you enable TILFA, because if we have not enabled the TILFA, then nodes actually they rely, first they are just going to send the traffic to alternative link. This could be towards 13 or this could be towards 9. But once the IGP protocol actually converge, when I am saying converge, that means it's going to realize the failure and it's going to calculate the shortest path again by excluding this link, and it's going to calculate the shortest path towards 15 from here based on the information it has, and it will again need to calculate the latency. So this information is going to share with the controller, and then controller can calculate the new path which satisfy our requirement. But think like how much wait we have to do. First we have to wait for the convergence of the IGP, and then controller will receive this information from the IGP, and then it's going to share the revised list of segment. But this is not maybe our desired outcome, or we do not want to wait for this, because obviously if we do this, then we are going to have the packet loss, or maybe our objective is not getting fulfilled, because when it's going to send the traffic using the alternative links it has, it is sending and it is reaching, but after the convergence we get the optimized path, which is not the same path which it has used during the failure. Like when it was providing us the alternative path. It has selected the path which is having the higher latency, and after the convergence it has given us the optimized path which is different than the path which we were using during the initially we were using after the failure. That's mean now another switching will happen. If the traffic was going from here, then after receiving the optimized path, it started going from here. So the traffic will switch from here to here. But if we use the TILFA, then it actually pre-computes the optimized path. Like after the conversion, what path will be, it actually pre-computes and keep it ready. Once any failure happen, it use the post-conversion optimized path. So it is just like this. We are going somewhere, okay, and we see, okay, there is a container, road is blocked. We say, okay, take any of the path whichever is available, go right or left, because we cannot go further from here. But after traveling somewhere, we then realize, okay, we are maybe going on a path from where it will take more time. So what if we take another optimization and take a U-turn, or maybe take a next turn and go on a certain path which is most appropriate. But in this case, we are saying when we see a failure, we see an obstacle, at that time we are taking the path which is optimized path. By excluding this, by considering this failure or considering the obstacle, we are taking the most optimized path when from the first reaction. Like when we are saying, okay, take right or left, so we are taking the most optimized path, not just avoiding the failure. So this is the advantage of using the TILFA topology independent loop free alternative. When we use it, then it gives us this ability within our network. And another thing, in case of so this is the example for the TILFA. Like we want to go from S to D. So this is our source, and we want to go to destination D, and this is our network. So you can see the metric we have defined across our node 100, 40, 40 and 10, just to make it like feasible for our scenario. So in this case, traffic from S to D takes the shortest path via the R1. When we say the shortest path, you can see this is 20, so it will take the upper path. So this is our shortest path before the convergence. When there is no failure, what happens if the S to R1 link fails? Okay, so then S1 need to send traffic towards D using the two alternative paths. So the traffic on the S going towards D, it is dropped while the convergence is happening if we do not like implement any kind of protection. So it will keep on sending because it is considering still it is active unless it detects it, and detection could happen through the use of BFT or your IGP protocol actually inform the router that I am down, and then it can remove the destination using the R1. So in case of post conversion, when the IGP protocol has converged, then traffic will go over this link, because here we have the this is not the shortest path. This one become the shortest path because this one is not available now. So how TILFA can protect the link from S to R1? So there could be two possible alternative to reach to the next hop. If S1, if there is a two next hop, and the S to R1 link has to be protected. If we want to protect this link, there could be two alternatives. One is this one, another is this one. So in this case, in case of TILFA, if the R1 needs to protect the traffic, it has to satisfy two of the criteria to become the alternative node which can provide us the connectivity towards D. So one, this is a criteria, like it has to, we can reach to D from where it does not rely back on this link. And another thing, it has to specify, like we can see from here. So it has to be greater than like R to D, and if we calculate R2 to S and then we consider S to D, so it should be less than that, which is not true in this case. That's why it will not fulfill the requirement. So secondly, we also take into consider the downstream criteria, the other router, where R2 to D should be less than from S to D. So in short, just because of the time, we will not be able to go into more detail. So I will go to the last slides where we have about this. So actually we need to calculate Q space and P space in this case, and see the node which is actually where Q and P space both are interacting. So the Q space is the list of the nodes from where we can reach to D without going back through the source, and our P nodes are the nodes from where we can reach to S without like reaching, depending on the failure, without like using the destination. So the node in this case where the P and Q space will interact, this is actually the node which actually, if we send traffic to this node in case of failure, then this will be our post optimization path. So that's why if the failure will happen here, so we are going to send traffic towards R instead of sending towards R2, because this will be the node which can satisfy this. So let's try how the S1 will protect. So the step 1 is to determine the P space for S with respect to S and R1 links. So in that case, this will be the like the criteria, or this will be list of the nodes which can reach to D without going back to the S. So if you want to reach to D, like you can reach from R2, R3, R4, and you can go from the like R7, R6 and R5 as well. So this will become your P space, and the so in order to determine the Q space, you have to see how you can reach to D without going back to this link. So actually you have to find the common node from where you can reach to destination and source without going back to the link which has failed. So there should not be any loop, because if you select any other node which will be depending on this node based on the metric, then you face like it will be either a loop or it will be not the post convergence loop. So in short, in this case, it needs to find the PQ node, or the node where the P and Q are interacting, and it will select it as a best node. So this will be your Q space and P space, and it will see where it is interacting. Then it will like again it will find out, so it will be the R5 node once it like cross them. So this is the common node from P side and the Q side. So this will become our PQ node, and but in this case this is like maybe the post convergent path is not there. So if your actually there is another concept. If your PQ node is not on the post convergence path, then there is another way. It needs to determine the extended P and Q space with respect to the failed link, and then it needs to identify it. So in case of extended P space, it will again consider, it will like exclude, it will see from with respect to S, the S1 and R1, and in this case it can see the R2 and R3. These are the two nodes. If it select them, it can reach to D without going back to this link. So it will select R as a P node, and this is the closest to the destination, and we could easily like justify if we choose R2 in this case, because if this is becomes over your shortest path. Earlier if we select R5, but this was not the optimized path, that's why we have to select the extended PQ space, and R2 will become our like the optimized, it will be on the optimized path. So if you will send the traffic to R2 only, it will eventually reach to D without going back to source, and the traffic will stay on the same path. In case of even the IGP will converge, but it will also report the same node as a best node to reach to the D. So you can think about the metric like here, from here, if this link fails, after that, if you just send traffic to R2 based on its SID, so once it reaches to R2, because this is the shortest path, from here we have the higher metric, it will reach to R2. From there, it has like 10, 40, and again 10, it will be 60, but from the other side, the metric is higher. So we need to send towards R2, not to any other node, to so the traffic will remain on the optimized path even after the failure. So you do not need to calculate it. It's the controller who is going to pre-compute this for you if we are using controller in your case. Okay, so we can go for break, and so when we should resume?